Okay, so hello everyone. I am Pulkit Verma from Arizona State University, presenting the work Asking the Right Questions, Active Action Model Learning. This is a joint work with Shashank Marpally and Siddharth Srivastava. So, if you have an autonomous agent, how would you determine that it is reliable or even safe for a certain task? Especially in the cases when you don't have the access to the agent's internal model, meaning that it is essentially a black box for you. In such scenarios, if you have a person, you can simply interview them. But could we do this for an autonomous agent? And if so, what queries will we ask? So for this, let's see an example scenario. So this is Alice, and she is an expert in biomedicine. Now she gets a new robot, which is a black box to her. Now, how can she determine that this robot is safe to use in a lab? If this was a human assistant, she could have interviewed, as I said earlier. But from a user's perspective, there's quite a lot of research on like how to get agents to answer questions effectively. But AI systems have different failure modes and performance profiles than humans in general. So it will be very difficult for Alice to figure out which questions she should ask and how to extrapolate the robot's capabilities from those responses. Now, to solve these issues, we propose an agent assessment module that queries the agent and receives its responses. Now, this module takes as input the user's preferred vocabulary, and like these are the terms that the user understands. These can be predicates. And at the end of the querying process, the model returns a user-interpretable model. And the user gets an understanding of the agent's capabilities after this whole process. Now, in this framework, the agent need not know this vocabulary or the user's modeling language, and it can have an arbitrary internal implementation. Also, the user knows the names of agent's primitive actions, and even when it is not known, like we can, like without loss of generality, the first step can be like listing of names of these actions. Now, these assumptions on the agent are pretty common, and in fact, simulators are already used for verification, and their instruction sets have to be reviewed for their usability in such cases. Now, this paradigm also assumes that the agent can be connected to a simulator, which can help the agent in answering the queries. So now we'll see like what a typical interaction will be like. So here the agent assessment module could ask a query to the agent on behalf of the user, uh, like asking what will happen if it must perform a set of actions in a certain situation. Now the agent uses its own internal mechanism or a simulator to respond to the query. The assessment module can ask such questions multiple times until it understands the agent's capabilities and estimate the complete model of the agent. One of the major technical challenges and our main contribution here is to ascertain like what queries to ask and in what order we should ask them. So now we'll see like how we overcome these challenges. So at a very higher level, we generate an interrogation policy and use the agent's answers to estimate its model in a user interpretable vocabulary. In the context of the specific work, user interpretable means strips like because such models can be easily translated into interpretable descriptions. Now let's see why. Like so, here on the right, you can see an action in strip-like form. It indicates that if the precondition holds and the agent executes the action, the effects will occur. If the action is executed when the preconditions don't hold, then nothing will happen. In this case, it's saying that the agent will be able to pick an object if its hand is empty and the object is on the rack. And after executing the action, its hand will not be empty anymore and the object will not be on the rack and the agent will be holding that object. Now, such models have an advantage that they are clearly predictive and they also allow counterfactuals and assessments of causality. These are also easy to convert into natural language. But one of the major problem is that there are too many such models possible, and like actually exponential in terms of actions and variable instantiated predicates. So now we will see like what a query looks like for our work. So formally, a query can be viewed as a function that maps models to responses. In our work, we use a specific class of queries called plan outcome queries. So these queries ask an agent like what it thinks will happen if it executed a certain sequence of actions, like we call it a plan, in a certain initial state. Now, using its internal model, the agent responds with the length of the successful execution of the plan and the resulting final state. So now the next question is like, how do we generate these queries and how we use them to infer the agent model? So what we use is the concept of abstraction. So we take two abstract models and generate queries that like in a such a way that their responses can help in distinguishing between these two models. So now we'll see what kind of abstractions we use. So now let's assume that we have this concrete model on the left, and on the right, you can see a possible abstraction of this model. Now, since abstraction loses information, here the information about how on-table appears in action pickups precondition is lost. So here positive, negative, and empty indicate that on-table predicate might be in positive, negative, or absent form in precondition of this action. So now we will see like how we'll use this in an algorithm. We will try to predict the model of an agent having the internal model set to this model shown here on the left. So now for each action, as I said earlier, the predicate can appear in two locations, precondition and effect. And we name such predicate, action, and location combinations as N1, N2, and so on. We also start with this most abstracted model, which is shown here in green. At this level of abstraction, we do not have any knowledge of how any predicate appear in any action at either precondition or effect. So we go ahead with the concretization using any one of these at a time. We can choose to refine them in any order. So for this example, I'll go in alphanumeric order, N1 to N4. So here we can add hand empty to the empty models. So in the precondition of pickup action in three forms, positive, negative, and absent. So here we show these three refined models as MA, MB, and MC. So now what we do is we pick two of them at a time, and like we can pick them in any random order and generate a query which can distinguish between these two models based on their responses. We reduce this query generation to a planning problem. I will not go into detail that how it's done, but you can refer to the paper to see how exactly we are creating this planning problem. But for now, let's assume that it is possible. Now we pose this query to the agent, which responds using its own internal model or a simulator. Now we check the consistency of the responses of those two models with that of the agent. And based on this, we can reject one or even both of them in some cases. Now let's assume that MA's response was inconsistent with that of the agent. So we go ahead and prune that. And then we take the other two remaining models and generate a new query. We again do the whole process, like we again reject the inconsistent refinement. Now, remember that at least one of these three will always be consistent with the agent, because that would correspond to the correct model of the agent. An advantage of this approach is that at each step, we know exactly what we do not know till that point. So at this stage for pickup action, it is not known like how on table appears in both precondition and effect, and how hand empty appears in effect. This approach also provides convergence guarantees, as after refining each of these predicate action location combinations, like this N1 to N4, we reduce the set of information that we do not know. So this is hard to determine if we are learning passively from some previously observed data. So now let's see why this approach leads to less number of queries. Now, remember that when we refine in terms of hand empty, we created three models, MA, MB, and MC. We show them here in three colors, gray, green, and orange. So now what would have happened if we didn't prune it at that time? So in that case, we would have had 9 models at the next level to consider and ask queries to. And like these are corresponding to 3 different concrete versions of each of those 3 abstract models. I think you can see like where this is going. Like by the time we reach the most concrete, like the most concrete level, we would have had a very large number of models. Like to be exact, 9 raised to the power number of predicates times number of actions. So when we prune a model at an abstract level, what happens is that all the models that would have been its possible refinements are pruned out. And by the time we reach the most concretized node, we have just 3 models in most of the cases. So a key feature of this algorithm and the central idea of this approach is that we are generating queries and pruning out models at abstract levels. Hence, we keep the interactability of the approach in check and end up asking less number of questions. Now we'll see some approaches which solve similar problem. Okay, so several approaches have been developed for learning interpretable models. Some of these use passively observed data as input, and the prominent ones include ARMS using weighted max set problem to learn this action model, LOCM, which uses finite state machines, LOUGA, which uses genetic algorithm, and Verma, which uses a custom planning problem to learn the action model. Now, but one problem of these methods is that they do not feature any interventions like during their inferring process. So hence they are susceptible to learning buggy models. So for example, if you have a robot that picks up only blue beakers in training, these approaches might learn that a beaker has to be blue for the robot to pick it up. Now, of course, with more input, these might learn the correct model, but there is a dependence on the input data, like whose generation is not controlled by these methods. Also, recently, Bonnet and Kepner proposed another approach which takes as input one or more labeled directed graphs, which encode the structure of the state space of those problem instances. This work requires no symbolic information, but is more suited for smaller problems because it generates a very large set problem, which becomes infeasible to solve for very large problem instances. For comparison of our work, we use Verma. You can refer to a paper for a more extensive survey of the related work. But for now, I'll quickly go through how we evaluated our algorithm empirically. So we tested our algorithm on 2 types of agents using symbolic sims, that use models from the International Planning Competition as the internal model, and agents using black box sims that report states as images using PDLGM framework. As I mentioned earlier, we use Verma as the baseline for comparison. This method Verma takes as an input a set of plant traces and learns the action model that conforms to those input traces. Now, since the focus of our approach is on automatically generating useful traces, we provided Verma with randomly generated traces on the same problems that we use. Now we will see how symbolic and black box sims work in more detail. So for the agents with symbolic sims, we initialize the internal model of agents with one of the 10 IPC domain models, and then we let the algorithm estimate the model of the agent. Obviously, the algorithm did not know what the actual model was. Then we evaluated the performance in terms of the accuracy of the learned model, the number of queries asked to the agent, and the time it took to generate those queries. We then compare the results with Verma in terms of stability of the models that are learned and the time taken per query. So here we showed results for the agent in the Bloxword domain. So the solid lines show the model accuracies and the dotted lines show the time taken per query measured in seconds. Here our algorithm was able to learn the correct model with just 48 queries. And as you can see, the Verma's accuracy keeps fluctuating because it is not guaranteed to converge to the true model. And this would make it very difficult to determine like when to stop the learning process, while in our approach, the convergence is guaranteed. Our approach also took less time as compared to pharma. In another domain called termies, which has negative preconditions, pharma again did not converge to the correct model as it ran out of memory as we were increasing the number of input traces. Here, our approach was able to learn the correct model with 134 queries. And also note that the time taken was not as much as pharma again. So this table on the left shows the detailed results for all the 10 IPC domains. It includes the number of queries asked, average time taken per query, and like variance of time taken per query to learn the correct model. To solve the planning problems, we used every planner with LM-cut heuristic. As you can see, for all the domains, our algorithm took less than 550 queries to learn the correct model. Also, except for free cell, our algorithm managed to learn the correct model in less than 25 seconds per query. So now let's see the agent with black box sims. We initialized the black box sims with one of the two domains, SOCO1 and DOORS, provided by PD Tails in framework. On the right, you can see these domains, SOCO1 and DOORS. Now, similar to symbolic sims, we let our algorithm estimate the model of these agents. Now, these agents reported the states as images, like they only gave the final state images output. So the assessment module extracted the states from these images by using image classifiers for each predicate. We assume the image classifiers should be noiseless for this work. Now, on an average of 5 runs, our algorithm correctly inferred the Sokoban agents model with 217 queries, and for DOORS agent with 188 queries. Now, to conclude, we propose an approach for efficiently learning the internal model of an autonomous agent in steps-like form through query answering. And to achieve this, we use model abstraction and AI planning. Note that this method needs no prior knowledge of the agent model and requires only the agent to have a rudimentary query answering capabilities. And finally, this learns the correct model in user-interpretable vocabulary with a small number of queries and in lesser time as compared to the closest related work that was Verma. In future, like we can extend it to handle noisy classifiers or to replace communication interface with natural language. After this Q&A session, if you have any further questions, feel free to drop us an email, and you can find the paper at this particular link. And we also had this paper in the main track of AAAI 2021. You can access that using this particular link. Thank you. Like I can take questions now.
Thank you, Pulkit. Very interesting work. So any questions? Anyone? Let's check if there's
if there are no questions, I have one.
Yeah.
Is more like curiosity. So could you please define a bit more the notion of abstraction that you use it in this work?
Yeah, so a model abstraction, like an abstraction of like a model is something which loses some kind of information. So for example, if I have a robot which uses some sort of inverse kinematics, but then I can abstract the whole concept and say that, okay, robot can go from this particular initial state to this particular initial state, like it can move its arm, right? So now this capability I can completely abstract, like I cannot mention the underlying inverse kinematics at all. So like when we abstract any model, some information is lost, right? So that I showed, let me go. So here, right, so at this level, I do not know like how on table will appear in the precondition. So a model saying that, okay, whenever my hand is empty, I can pick an object. That is an abstract model because it abstracted out the information that the object has to be on the table at that particular time. So here I'm losing some information.
Okay. Okay.
I think Tathagata has a quick question. Maybe you can ask.
Can you hear me?
Yeah, I
Yes.
can.
Yeah, I had a question about the setup itself. Like
Okay.
the generated queries, who are they for? Because the user will always ask what they want, right? And the query generation system, like regardless of minimizing the number of queries to get to the model, it's not like we are generating the questions for the user as well.
Yeah. So the questions we're not generating for the user. So here the questions are for the agent, right? So the user just tells that, okay, I want, I understand these predicates, like I can understand these concepts. I want to know the agent's model in terms of these concepts. So the agent assessment module knows what actions the robot can take or the agent can take, and it frames questions to the agent. And based on the answers by the agent, it comes up with the model in terms of that, for what the user can understand in terms of those predicates.
Thank you, Pulkit. I think that's all the time we have for questions. Thank you very much again for the talk.